Just like with all other statistics problems, we have a 4-step process for doing confidence intervals, whether it be for proportions or for means. The 4-step process goes like this. As always, we have our state. And when you state, you want to include the parameter that you're trying to estimate, as well as the confidence level that you're wanting to estimate at. Okay, then the next step is the plan. And when we plan, we want to always identify the method. And you can do that by saying the name of the confidence interval. So the one that we have been talking about is the one sample Z interval for proportions. I like to just write the formula down with the symbols plugged in. So p hat plus or minus z star times the square root of p times 1 minus p all over n. That works just as well as saying the name. The other thing you want to do in the plan step is to check your conditions. Okay, remember our conditions are random, normal, and independent. Then we want to do the do part, which is where we actually do our calculations. And then we finally want to conclude. And when we conclude, we want to interpret the interval in context. Okay, remember we always do everything in context. And when we interpret the interval, that's the saying we are such % sure, confident that the interval from blank to blank captures the true value of the parameter, and I talk about the parameter in context. So those are the 4 things we want to make sure we do. State, plan, do, conclude. Okay, is it okay to use your calculator? Yes, but you need to show all your work. If you're interested in using your calculator, and you have to make sure you show all the work, but if you're interested in using your calculator, you want to hit Stats, then go to the Test menu, and then on my calculator it's option A, but it's the 1 prop Z interval. And then that will give you the setup to actually find the interval on your calculator. So let's run through the 4-step process with this problem right here. Okay, it says, according to an article in the San Gabriel Valley Tribune, most people are kissing the right way. That is, according to the study, the majority of couples tilt their heads to the right when kissing. In the study, the researcher observed a random sample of 124 couples kissing in various public places and found that 83 out of 124, or 66.9% of the couples, tilted to the right. Construct and interpret a 95% confidence interval for the proportion of all couples who tilt their heads to the right when kissing. Okay, I'm going to talk through this more than write because there's not a lot of room here, and it's hard for me to write in small spaces for these videos. But I'll talk you through it. So the first thing we would need to do is state, and we would want to state 2 things. We are wanting to estimate the proportion of couples who tilt their heads to the right when kissing. Okay, that's the parameter. And then we need to say at the 95% confidence interval. That would be our state. So then to plan, okay, for our plan step, we would say we are going to use the formula p hat plus or minus z star times the square root of p hat times 1 minus p hat all over n to calculate this confidence interval. We need to check our conditions. Remember that our 3 conditions are random. Okay, this is met because it says that the researcher observed a random sample. So random is met. To do normal, remember, I need to do n times p. So that would be 124 is my n, times p, which is right here. That would give me 83, so that's greater than 10. And then I say 124 times 1 minus this, which would give me 41, which is also greater than 10. Then I need to say independent. Okay, this is sampling without replacement, so it's not independent on its own. But what I can say is that because there's only 124 couples in the sample, I can be sure that there are more than 1,240 couples total. So all of my conditions are met. So then I can go ahead with the do process, and I want to make sure I write this interval out with the numbers plugged in. So that would be 83 over 124 plus or minus my z star. Okay, to do my 95% confidence interval, I need to go do inverse norm and type it in on my calculator. And I happen to know that that one's 1.96 times the square root of p hat, which is 83 over 124, times 1 minus p hat, which is 41 over 124, all over n. So then I plug that into the calculator, and I get the interval of 0.586 to 0.752. Okay, so then the last step would be to conclude, and we would say we are 95% confident that the interval from 0.586 to 0.752%, that the interval from 0.586 to 0.752 captures the true proportion of all couples who tilt their heads to the right when kissing. So, that's the 4-step process. Okay, we talked the other day about there being 2 ways to reduce our margin of error. Okay, notice here that this confidence interval is pretty wide, from 0.586 to 0.752. Okay, our statistic, or our p hat, is going to be right in the middle of it at 0.669. So we end up with about a 0.083 margin of error if you go from 0.669 to one of the ends here. So that's like 8.3%. So there are 2 ways that I could reduce that margin of error and make this interval smaller. One is to reduce this confidence level. But often I don't want to do that because that makes me less confident in what I'm doing. So the other is to increase the sample size. There's actually a formula for margin of error where we can actually solve for our sample size that we would need to get a specific margin of error. And it's just the stuff that's after the plus or minus, because this is what represents our margin of error. Our statistic plus or minus the difference, okay, the margin of error. So my margin of error formula means that z star times p hat times 1 minus p hat all over n, and then take the square root. Okay, that would be my margin of error. However, I have a problem, and hopefully you're saying, well, we can figure out Z star based on the confidence level, but I have no idea what P hat is because I'm doing this at the very beginning, and I've not even taken my sample yet. Well, you would be right. So we need to say, okay, what is the worst possible scenario? What is the P hat that I can pick so that this would be the largest it would ever possibly be, so I know that when I make this sample size, it's the maximum that I would need, so that this is always less than or equal to the margin of error. Well, that value for P hat that you always should pick whenever you're doing this is 0.5. Okay, if your proportion is 50% or 0.5, then when I multiply P times 1 minus P, I'm going to get 0.25, which is going to be the largest possible value. 0.5 is always what you should pick if you are doing this process. So let's look at this example. Suppose that we wanted to estimate P, which is the true proportion of students at your school who have a tattoo, and we want a 98% confidence level and a margin of error of no more than 0.1. So that's when I use this formula here to figure out how many students I should survey. So when I use this formula, I say I need my z-score, my z-star, for my 98% confidence. So the first thing I need is my z-star, and so I plug that into my calculator, and I get the inverse, I say the inverse norm of, and I can either say 0.01, because that's half of the 2% that's left, or I can say 0.99, because remember I want the middle 98%, and so that means that this right here is 1%. So if I went from this z-star value backwards, that would be 0.99. And it gives me a z-star value of 2.33. And then I say times the square root of 0.5 times 0.5 all over n, because n is my sample size and that's what I'm solving for. That's less than or equal to 0.1. So then I solve this, and I'm going to divide by the 2.33 and then square it, and then basically multiply both sides by n and then divide by what's there. And so I'm going to end up with 0.25 divided by 0.1 divided by 2.33 squared. So when I solve that out, I get 136. Well, really I get 135.7, but since you can't have 0.7 of a person, you say my sample size needs to be greater than or equal to 136. So that's how we can determine the sample size that we need in order to get a specific margin of error and a specific confidence level. Okay, so now we are going to transition a little bit and start talking about means. We've covered everything we need to talk about with proportions, so let's talk about the other type of confidence interval. And there are actually two different situations you have when talking about a population mean. One is when you know the population standard deviation, and the other is when you don't. And the reason that this is a big deal is if we think about our formula, statistic, so the statistic would be x bar, plus or minus confidence, well, the critical value, times the standard deviation of the statistic. Well, for mean, the standard deviation of the statistic is the population standard deviation divided by the square root of n. So I have to know my population standard deviation in order to be able to do this. However, this rarely ever is the case. Since we don't know much about our population, in fact, that's our whole goal, is to predict things about our population based on our sample information, it's very unlikely that we're ever going to know the actual population mean. So then we have to substitute it in with something else. And we'll talk about that in a second. But what we can use it for, in fact, this is so unlikely to happen that there's not even a calculator command for it. So if it ever does happen, you actually have to type it all out on your calculator. So what we can use this for is to do what we just did and pick a good sample size for calculating a confidence interval. So just like before, this is still our margin of error. Everything after the plus or minus. And what I can do, not knowing the population standard deviation, is I can look at some previous studies or pilot studies and see if they have a standard deviation that I can use for a good estimate. And in this case, if we look at this example, administrators at your school want to estimate how much time students spend on homework on average during a typical week. So that means they want to estimate the mean at a 90% confidence level with a margin of error of at most 30 minutes. A pilot study indicated that the standard deviation of time spent on homework per week is about 154 minutes. So that is my sigma that I can use. How many students need to be surveyed to estimate the mean number of minutes spent on homework per week with a 90% confidence level and a margin of error of at most 30 minutes? So if I plug these things in, if I want a 90% confidence level, that means that my z-star value is going to be 1.65. And I get that by plugging into inverse norm, either 0.05 or I get it by plugging in 0.95. Then I say this standard deviation that they gave me from the pilot study over the square root of n, and I want that to be less than or equal to the 30 minutes. So then when I solve this, basically I say 1.65 times 154 divided by 30, and then I square it all. And I end up with 71.74, which means that n has to be greater than or equal to 72 in order for me to accomplish those goals. Okay, more likely than knowing the standard deviation, I'm probably not going to know the standard deviation. So that's what happens down here when the standard deviation is unknown. And what happens is it's very similar to what we did with proportions. If I don't know p, I plug in p hat. Well, if I don't know the standard deviation of the population, what I can do is I can say x bar, and let's actually do this in another color to make it stand out. X bar plus or minus the critical value, which we'll get back to in a minute, times, and I can use the sample standard deviation over the square root of n. Okay, the thing about using the sample standard deviation, and this is an S, not a 5. The thing about using the sample standard deviation is that it's going to change every time I take a sample, which is going to make my distribution act in a different way. And so if you were in class on Wednesday or Thursday during the block day, we played calculator bingo, and you should have noticed that hopefully using the sample standard deviation gives us values that are way bigger and way lower than the 3 and negative 3 that we expect our boundaries to be with a normal distribution. In fact, this, when you plug in the standard deviation, uses what we call a t-distribution. And the difference between a t-distribution and a normal distribution is, you can see down here on this picture, okay, the t-distribution is shorter and has more area in the tails. So there's more data in the further standard deviations away than there are with the standard deviations that we have come to know and love, of 99.7% of our data being between 3 and negative 3. So when we're using this, our critical value, instead of being a z-star, becomes a t-star. Okay, this still follows the same general formula. Statistic plus or minus critical value times the standard deviation of the statistic. Okay, so what statistic follows a t-distribution? That's going to be x bar. As long as a couple things happen. Okay, population has to be approximately normal. Has to come from a population that's approximately normal. And we need to not know the population standard deviation. So we have to be using the sample standard deviation. So as long as you are using X bar to look for the population mean, it comes from a population that is normal, and we're using the sample standard deviation, then you are going to use a t-distribution. So this is for when we don't know sigma. Okay, so let's talk about the shape, center and spread of a t-distribution. Shape, it is still unimodal, and it is still symmetric, but it is not quite normal. And we need to stop for a second and talk about something called the degrees of freedom. Okay, because of the standard deviation, DF stands for degrees of freedom. Because the standard deviation is from a sample, then depending on our sample size, we have what we call degrees of freedom. Degrees of freedom can be found by saying n minus 1. So it's always one less than the sample size. And you'll notice here that this dotted line has 2 degrees of freedom, and the blue line has 9 degrees of freedom, and then the purple line is normal. Okay, our standard normal or our z distribution. The more degrees of freedom it has, the closer it looks to the normal distribution. So the t-distribution actually approaches the normal distribution as your degrees of freedom get larger. Okay, your center is 0. It is still centered at 0, just like a normal distribution is. The spread, however, we can't really talk about because it depends on the degrees of freedom and the size of your sample, but we know that it is larger than the normal distribution, or the standard normal distribution, which is the z distribution. And we know this because when I calculate the margin of error, or when I calculate the confidence interval for X bar, there are 2 things that I don't know. I don't know the standard deviation, and I don't know the actual X bar, or the actual population mean. So therefore I have 2 variables that I don't know instead of 1, and so therefore my spread's going to be larger because the more variables you have, the more variation. So let's say that we wanted to construct a 90% confidence interval for the population mean with a size of 10. Okay, this doesn't tell me anything. It tells me it's a normal population, which is important. It does not tell me that it is that it has the population standard deviation. So I know that I'm going to be using T star. So here's how I find T star. One way to find T star is table B in the back of your book. And I don't have any way to show it to you on the video, but look at table B, and if you have any questions about how to use it, make sure you come ask me. The second way is on your calculator, and it's in the distributions menu, and it's called inverse T. Okay, and there's 2 things you need to enter in on inverse T. In the idea behind the confidence interval is the same. I would want 90% of my data to be in the middle, which means there's 5% here and 5% here. However, with a t-distribution, it only works if I enter in this value. Okay? The normal distribution will work for either this one or this one. but your t-distribution must have this one. And so I figure out the area from there to there, which is 0.95, and I enter that in first, and then I press comma, and then I have to put in my degrees of freedom. Because my sample size here is 10, my degrees of freedom is one less than that, which is 9. And so it would give me a t-star value of 1.833. So if we look at this example, this time we want a 99% confidence interval, and we want a sample size of 75. So one, I could use table B, or 2, I could use the calculator. Okay, a note about table B. If you look at table B, it doesn't have a row for 75. It doesn't have a row for 75. What it has is it has a row for 60 and it has a row for 80. Well, we can't assume that we have a sample size larger than what we really have, so we have to go one back and use the one for 60. So if I'm looking for a 99% confidence interval on table B, I would have to estimate that my t-star value was 2.66. So with table B, it would be about 2.66. If I use the calculator, okay, this time it's the middle 99%, which means there's a 0.5% here, which means that this from here down is 0.995. So I would say inverse t, 0.995, comma, and then I could put in my 74 degrees of freedom there. And I get a t-star value with the calculator of 2.64. Okay, the difference there is solely because of my degrees of freedom. And it is a, not a big difference, but it is a difference. So if you get one and you don't see the degrees of freedom on table B or whatever, just make sure that you specify whether you're using the calculator or whether you're using table B. And you have.